Hey everyone, welcome to the part 6 of the streaming series. Thank you everyone for participating and tuning in for the last 5 and for this one. And obviously we'll be looking into other streams in the new year. So again, this is part 6. This will be a continuation of what we touched on last week with primitive, but this will talk about a different method of initialization, looking at different invariants that are system-wide, and looking at end-to-end. Engineer 2 at Bits. We help developers build safer software. So we're using the latest programming techniques, and then using that to seed in research, in audits. And we work on a variety of tools such as Slither, static analysis for Ethereum, Echidna, which is the focus of these streams, as well as a variety of other chains such as Taylor, Amarna, and helper libraries such as Loxy Select. On the stream today, we have a few people from Bits who Echidna, as well as also a list of Twitter handles that are just a good list of people to follow. And from the primitive side. So I will be going into a recap of fuzzing. So this is very similar to just to the material that we've talked about in previous streams. Just so if you are hopping in for the first time, you aren't just hopping in on unstable ground. I recap of primitive. This one will be a lot shorter than the previous week 5. And so I highly recommend it if you have any further questions about how primitive works or it's not fully clear, to watch that video as well. And those slides also have links to like the primitive white paper and the primitive primer, which help provide a lot more context as to just how we can think about writing invariants for primitive. I will be going into a brief overview of the architecture again, just so that we have a recap of what we're trying to test this time. And then obviously the fun part. This part's going to be finding invariants, a lot of stepping through code, just kind of commenting on it, finding out, what is the expected behavior of the code, and then we're going to write invariants for the rest of the time. So one main question that often comes up with fuzzing is how to start. And usually the best way to start is just to find the system properties of your system that you expect in just plain English. So this means just like looking through your system, understanding what is expected to happen. And so this gives you an idea of what your system is expected to do. Once you have that, then you can convert that into code. In this case, it's going to be Solidity, which is essentially what Echidna is able to, it's how we write property tests. So once we have those tests written, we can run Echidna, and Echidna helps us find bugs, essentially find all the corner cases that, or find the corner cases that might affect in ways that we don't expect it to. So another common question that comes up is the difference between unit testing and fuzzing. With unit testing, we can potentially generate a random input, but it's not going to be as conclusive as it is for fuzzing, because fuzzing is going to use heuristics. Example being like the lower bound and upper bound of like an integer number to test a function, and we're specifying properties that we expect that function to hold. So if it fails, then it means one of our properties has failed, and Echidna would have found a bug within whatever target code we're looking at. Echidna is versus other fuzzers. Echidna is quite a bit more mature development for a number of years. It gas assumptions. So if you have certain functions gas than others, Echidna allows you to be able to run tests against that to differentiate functions and figure out whether there are components that you might be able to slim down or think about refactoring. It works with any compilation framework, which means you don't have a framework. You can pretty much just pick it up, write your test in Solidity, and then be able to test against that. It also supports various APIs for testing. For last week, for part 5, we mainly did pretty much internal testing, where we were testing kind of a stateful library contract. For this week, we're going to be looking at a different form of testing, just to in terms of initialization. It also supports a variety of HEVM and DApp tool cheat codes. So just to recap on, better to start with what we saw last week. We started with one of the helper libraries, actually out the core protocol, and that helps us understand kind of the expected behavior of the system. The other tip is to analyze pretty much all of a function. So this helps us understand, once we understand what a function's supposed to do, write tests against it and reason about what's expected to happen. Another thing that's important to keep in mind of testing that we're going to be doing today is determining in functions in general, because in arguments, it becomes very useful to determine what is a safe bound. Once you know that, then you can also based on that. Another thing to keep in mind within systems, and this is similar to a bug that we found last time, is related to functions that are inversely related. So if a function does one thing like add money to a pool and then does the opposite, like take money out of the pool again, this is good to keep in mind, so that you have an idea of what to test within your system. The previous point about analyzing kind of preconditions and postconditions, also analyzing what is the expected happy path for a user and what is the unhappy path and what is expected to happen in an unhappy path. Knowing and keeping that in mind can help you write and identify where these invariants are. So I did mention preconditions, actions, and postconditions. I'm just going to recap what they are because we're going to be filling in our invariants by thinking about what these preconditions and postconditions are. So the precondition is essentially being able to scope down the input space and narrow down what is the considered safer bounds that you want to test. The action is the function that you expect to call, and the postcondition is what is expected to be true after the action. And we're going to be looking at a variety of tests that check all different types of preconditions today. So this is a screenshot of what the coverage looks like from Echidna 2.04. The stars on the right-hand side next to the numbers, these identify all the lines that were hit with Echidna, and it's also, you can see with the green color. The R is all of the functions, all the lines in this file that reverted, and you can find those with the yellow. And then all the lines that weren't hit would essentially be marked in red. This provides a graphical what functions have been touched and what haven't, and this will come in handy afterwards. So just this, I did mention this last time. Um, these last two streams are very complicated, so I highly recommend you clone the repo, follow along with like what I'm coding, what I'm writing, follow along with like what the invariants are, and this, of course, is recorded as well. So feel free to come back and replay any part as well. Um, I should also add that a lot of the comments that I'm going to be adding today have already been pushed to that part 6 repository, so you can also use those as reference. So with that, I'll go into primitive. And as I mentioned before, this is going to be a very fast, quick overview of the primitive ecosystem. And if you have more other questions, I definitely recommend looking at part 5, watching that video, as well as looking at the primitive documentation and white paper. So from a comparison point between Uniswap and primitive, in Uniswap, you have one price curve, and the prices of these tokens are essentially going to change on a swap. These pools don't necessarily have a concept of time. It's just the pool is created and you can start interacting with it. You can start adding funds, you can start swapping. On the other hand, primitive, the price changes on the swap and over time. And it's that time aspect that makes these invariants quite difficult. It means, with considering time, it means at expiry that the pool consists of one token. So there's essentially a state in which primitive, which within these pools, they have interactions with two tokens and the price changes. And then after expiry, it consists of an underlying token. So to kind of visualize what that means, within these purple lines, you can see these are all, this is the RMM. So this is primitive, and this pink red line is Uniswap. Um, this initial curve identifies what primitive what the curve is when it's deployed. So what it looks like. And over time, it's going to start flattening out until it's linear. When it's linear, it means this is the point. This is its maturity point, maturity time, and one asset is going to be priced essentially at a specified strike price. So that's a bit, it is slightly confusing. So basically, it relies on a spot price. So there's no concept of oracles, and the price will continue to change until expiry. So the price curve continues to flatten out until it's linear. So if we take a look at just a concrete example of what that means, if we have a pool consisting of USDC and ETH, note that the order of these pools does matter. So this is assuming USDC is the underlying token, and ETH is the quote token. If we specified a strike price of 3,000, then and a maturity date of 100 days, then we can see that the price curve essentially starts with USDC on the axis, with the other quote essentially the underlying on the ETH. But basically, at maturity, the pool will consist of only USDC, and the strike price will be 3,000. Whereas the price curve on this side will continue to change until maturity. This is where this curve is essentially the way that primitive prices assets within the pool, um, under the assumption that no assets can be bought and sold after maturity date has passed. So this is basically how to understand the concept of expiring assets. This tells you how much you're going. This is essentially the trading curve. And this is where a variety of other arguments come in to the picture of what makes a curve unique. And we'll be quickly going over that through the code in a little bit. So it means at maturity, assets can't be bought or sold, and it basically, in the example of a USDC to ETH pool, um, the pool only holds USDC, and the pool price is that USDC at 3,000. Um, any questions there so far? All right, perfect. Um, so I'll just go quickly into the system architecture. Um, this graph, if you saw part 5, will be very familiar. Basically, there is a concept of an engine and a pool within primitive. And last week we focused on a helper margin or reserves library that essentially found a bug within allocating and then removing from a pool because of the difference, because of a rounding error. For today, we're going to be focusing on deposit and withdrawal with an engine. So basically what that means is users can use that deposit function to put funds into the engine, withdraw to take funds out. Um, and assuming if you take a step back, the way a user would deposit funds into a pool would be either to call deposit and then allocate to a specific pool, or essentially use the allocate to deposit funds. The reason it was split up was due to saving gas costs, so that users could deposit at any time and not necessarily need to allocate immediately. Um, but for the purposes of today, we're going to be focusing on the deposits and withdrawals within the engine. So this is the high level overview of the current architecture of the system. So we have a primitive factory. The factory creates engines, and the engines essentially have tokens. This graph, obviously, there's a bunch of missing arrows here, and they're kind of implicit. But basically, they would be initialized with like the risky. This would be risky 6. These numbers represent the number of decimals. So basically, what we have here is assuming you were to use a factory to deploy an engine, um, we can potentially deploy like 4 different engines with a variety of different token decimals so that we can actually test the system. Um, that being said, due to complexity, we are just going to be focusing on an engine with 2 18 decimal tokens. So the risky token having 18 decimals and the stable having 18, and an engine with 18 decimals. So from there, we can go into system setup. How do we get this up with Echidna? And how can we make use of other tooling to help us deploy like a system that looks like this? Note that these are just 6 and 18 are the bounds in which the factory allows you to interact with tokens. So if you have a token of anything less than 5 decimals, you're not allowed to use that within primitive. So this specific example is just targeting essentially the permutations of the minimum and the maximum token decimal numbers within this system. So we can start with using Etheno. Etheno allows us to track deployments, and we can test against an end-to-end script. You can find the source code to Etheno within this website, but then you can also just install it through pip. What does Etheno actually help with? It helps us be able to take a deployment script out of like the testing library in a repository, allows us to run it against our local blockchain and actually save the addresses, which means with Echidna, we would be able to test that instance each time, as opposed to have Echidna need to redeploy the system. So with that, I'm just going to go through some of like essentially how we can get up Echidna with Etheno within this initialization. So um, first, we need to start Etheno. Um, Basically, we're starting it with a series of arguments that define start a local blockchain with a series of ganache arguments, one being deterministic so that we have the same like EOAs being created, and so we have the same setup of the blockchain with a higher gas limit. This just helps Echidna have more room, essentially have the blockchain has more room to play with in terms of finding different variations of functions to call. And this last -x is basically saying save the snapshot of the blockchain into this init.json file. Um, so with that, I'm just going to start um, Etheno. What this is going to do is just going to start this ganache network. It's using the CLI. It's going to have our gas limit that's higher, and then just the default like gas price, gas limits. This starts an RPC that's just on our local host, which means then we can just take a deployment script um, to essentially run our tests on. So this is one worked. Red Hat and Ethereum deploys in this case a token with stable token with 18 decimals, um, and then deploys this engine. So with the engine, we can go into um, in the previous in this slide said where we can bypass the factory and initiate an engine So this is essentially just walking through what we did to make those changes. Because if we look at the actual primitive engine, what it does is it takes the primitive, it essentially takes arguments that were sent from the primitive factory. So the actual engine doesn't have arguments, which makes it more difficult for us to test because the primitive factory uses like create two to deploy those engines. And we don't, Echidna has some doesn't really handle the create it doesn't handle the create two very. So what we can do is just call a Echidna version of the primitive engine and then just copy and paste the need for the library. What we're doing here is basically just saying um, send in the risky token, the stable token, the scale factors of the two tokens, which are used for the curve calculation and the minimum liquidity. So we're just going to save those. And because we're deploying the tokens ourselves, we're making an assumption that the token decimals, both tokens, is between 6 and 18. So this is an inherent assumption that we can make because we are controlling the deployment of contracts in this ecosystem, which means then we can just essentially deploy the tokens ourselves, add it engine. So risky, or for risky token, we're sending in just the risky 18 address. The stable, we're sending in the stable 18. Scale factor, we're just going to set to 1. And minimum liquidity is just going to be a random number. For purposes of this example, 1,000. What we can also do is essentially create tokens of other amounts, like risky of 6 decimals and stable of 6 decimals, and create a variety of different engines to test against. But for the purposes of this example, we're going to be focusing on this particular engine. So once we have we have this deployment script set up already, all we need to do is run it and essentially target it against the local network. So we can just copy this line. What this does is it's going to deploy the tokens in the 2 decimals. It's going to deploy the engine, and then it's going to the deploy scripts. It's basically going to print the addresses out. So we'll have it to reference. So this is the output. What we see is the engine has been set up with these values. The test token has also been deployed. Anything below this dash line, I'm just going to leave here in case you want to test engines of different decimals. But as I said before, we're just going to focus on the 18 and 18 setup. I'll pause there for now. Any questions about that? All right, perfect. So, okay, we have the addresses. It's not exactly clear what that means. So if we take a look at our deployments on the blockchain, we see a series of contract created. What we can do is hit Control C. This will shut Etheno down and then save the JSON within this the export file that we specified. So if we just take a look at that, I'm just going to leave word wrap off just because it's got essentially all of the extra data for data that was sent in. But what we have is essentially a series of contracts that were created, and a lot of these are the contracts that we're essentially going to target. What we can tell what those contract addresses are by what this printout is. We can see the engine, and we can see the token and the token addresses, which we can just copy into our end-to-end file. So here I've got placeholder values for the risky token and stable, but I can just copy in. These essentially mean they're not just addresses per se. These are the deployed contracts that we're actually going to be targeting. These are the contracts that we want to test. So it begs a good question. Okay, now that we have these contracts, where do we go next? Because there's a variety of things that we can test, but we want to make sure that it's been deployed properly. What we can do is just take another look at the primitive engine and just see how this constructor works. So the constructor takes in the 2 tokens, the scale factors of 2 tokens, and the minimum liquidity, and then saves them into like variables, immutable variables. So I'm just going to close this deploy. So once we see what this constructor does, then we can actually just test, write a series of simple tests to make sure that it's been deployed properly. An example of this is we can check the correct precision and the correct minimum liquidity that we specified. Again, if if someone were able to change the liquidity in some way, this would be a bug. We would have found like a case in which you are able to change liquidity, but you shouldn't have. So with that, we can shouldn't have closed this deploy, but we can take a look at the scale factor and the liquidity again. And we can actually just copy essentially the arguments that were sent in. So if we go back to precision liquidity, we see a scale factor of the risky token is 1, and the scale factor of the stable is also 1. So we can even just call the engine, start with like minimum liquidity has to be equal to 1,000. We can say engine dot scale factor risky has to be 1, and engine dot scale factor stable has to be 1. This is just a simple test just to make sure that the engine has been deployed correctly, which we can go into. I'll just open the README as well. We can run this, essentially remove the critic compile artifacts and cache directory, and then call Echidna test on the E to E, specifying a config. And I'm just going to run this first. And while that's running, I will walk through the arguments that were used within the config. So we can compile that first. We need to add brackets because this is retrieving the public. This is retrieving the scale factor risky object from here. All right, so that compiling, just going to let that run while we look at the arguments that are in the YAML. The corpus directory is similar to what we saw last time. It saves the corpus in this directory. One thing I should mention, if you are running this locally, I did add a corpus zip file just to make these runs faster. So if you are testing it locally, I would highly recommend unzipping this and being able to run the corpus. This is the init.json. This is where we're specifying where to seed the contracts. And just as a reminder, this is useful because this tells us essentially what the state of the blockchain is. If we were to not use, if we were to bypass, then the constructor would be incredibly complicated because we would need to, I'm just going to pseudocode this, we need to deploy a test token or like a risky token of 18 decimals. We would need to deploy a stable token of 18 decimals. In this particular case, we would need to deploy an engine of 18 decimals. But this is assuming, this is trying to keep this Echidna test reusable so that you can also then test pretty much any combination of engines. So if that were the case, then you would also need to add in, deploy this like risky token of anything between 6 to 18, and then engine combinations of like all permutations of 6 to 18, pretty much. So using Etheno within this code base helps us essentially be able to um, we're able to take an existing testing and deployment script um, and then test right against essentially the setup system already. And we don't need Echidna to create all the engines to set us up. Um, any questions there so far? Okay, I see. Yeah, so I think I might have just touched on it, but the question was what was the benefit of using Atheno again in this context? So it's in this particular context, it's good because Atheno is essentially the endpoint that helps us track and log all of the deployments within these contracts, which essentially logs it, prints that out to the JSON, and provides it to Echidna. So it's pretty much an auto deployment. um, if not, then if we didn't use Echidna, as I mentioned, we would need to deploy the series of all of the tokens that we want to test, and then deploy the engines of everything. Whereas allowing us to seed on top of this JSON allows us to essentially work off of existing test suites, and it keeps our Echidna tests clean as well. So while that runs, I'm just going to go back to this YAML. This YAML basically is the initialized flag is where we're specifying where to look for the state of the blockchain. This is like the in.json that was saved from that Etheno run. Test mode assertion, this is the mode that we are going to continue to use for this stream as well. We used it the last one as well. This one allows us to essentially test against assertions. So test a series of preconditions. Shrink limit, this will essentially determine how many times to shrink, like if Echidna found a failure, how many times to essentially iterate over making it smaller. We're just increasing the maximum gas as well as the code size just to give Echidna more room to work with. And filter functions, I'm going to come back to this. I'm going to come back to these two flags afterwards. Timeout, we're essentially just specifying like a timeout time for Echidna. While we have the precision and liquidity, another thing we can do, and this is useful for like testing the proper deployment in this engine of the engine as well, is that we can just assert that the engine's risky token is equivalent to like the risky token that we expect. This looks like a simple test, but if we start getting into engines with many different tokens, like for example, decimals of like 6 and decimals of 18 or 6 and 6, being able to check against the proper deployment is useful because we can actually make sure that all of the engines were deployed correctly. So I'm going to let that run while we look at the deposit. So the deposit, I've already stubbed out pretty much the what the safe case is, what the safe bounds are, but I want to walk through it because I want to walk through essentially how to write tests for the withdrawal. So if we look at the primitive engine, we look at the deposits. The recipient is specifying the address in which the margins for that user you want to add to. So basically, if I want to deposit into a system, if I specify my own address as the recipient, then it means my margins are going to increase. You're specifying essentially the deposit amount for the risky token, And this is similar to the allocate. So this concept is quite familiar. This is specifying the amount for the stable token. The data, we're going to ignore it for now. We can just assume it's going to be empty. And I'll talk about why afterwards. So just to walk through, this line, this if statement is checking whether the amount that you want to deposit into the system is equal. If either amount is equal to 0, then the system reverts. So basically, this tells us that like the del risky and del stable have to be greater than 0 for both of them. What it also does is call margins dot deposit with a recipient and the amount that you want to add to the system, which is going to increase the margins amount for the user. If we go into margins very quickly, this is very similar to what we saw with the allocate. It basically just increases the risky balance of that recipient and the balance stable. It's this, all of this code essentially executes a token transfer. This is where money is actually going to be sent from the sender to the recipient. So what it's basically doing is saving the balance of the both the risky and the stable token. This is the amount of funds that a user has before the next line. And this next line is where this interesting logic comes in with the callback. The callback is expected to have the token transferring logic. So it means the message.sender is expected to have like a callback that does something like risky.transfer, and I'll just pseudocode this from the recipient to the engine of like a del risky amount, and we can say the same thing about the stable. Which is why this check risky balance is basically going to ensure that the current balance that a pool holds is equivalent to what they had before, plus the amount that was added into the system. And this is said for both tokens, both the risky and the stable. So there's basically an inherent assumption that the callback is going to have this logic, as well as the same for the stable. Which brings us to the deposit function, which we can see we need a variety of data within this code, but we essentially need what the engine, what is the recipient's margins beforehand, so that we can check that it has increased. For this purposes, we're just going to bound it between between 1 and UN64. Note that the margins follows a very similar pattern to what we saw last time with the allocate, which was the function takes in the UN256, downcasts it to a 128, and then adds it to a data structure that's a UN128. So for this purposes, we're just going to narrow down our safe range within this function just to cover for max. And then if we were to do this like to be conclusive, we would say like have another deposit with like 64 to 256 or 64 to 128 and then 128 to 256. But for this purpose, I'm just going to assume that we're bounded to a middle of the bound. We're just going to, so this amount is basically specifying how much you want to deposit into the system. Now, in order to deposit, you need to actually hold tokens in the engine, which is what this mint tokens function does. This mint tokens, we can see it just it calls this helper, and it's basically just going to mint amount to the recipient, and in this case, it's address this. So it's giving ourselves essentially we're printing risky the amount of risky and stable within. Um, and then we're just going to save the balance snapshot. We can find it basically just holds the amount of risky and stable tokens that we have, retrieves the balance, and then returns it. So if I go back to deposit, what this is doing is basically save the pre-deposit balance of the sender, which is address this, and the pre-deposit balance of the engine. So just to reason about what exactly we're testing right now, I'm just going to go back to these slides quickly. So I did mention that there were essentially 3 different actors. One is the sender, which we can consider as message.sender, which in this test suite is basically address this. It's the Echidna E to E file. On all of the functions, the deposit and the withdraw, it takes a recipient address, and this is another role within the system. And the final role is the engine. So the engine is the one that's actually controlling receiving funds and then sending out funds, which is something that we also need to keep in mind. So this should help with identifying what the expected behavior within this should say state deposits within the deposits are. So when a user puts money into the system, they specify what the recipient is. They specify who the recipient is. And that recipient, assuming that they start off with a balance of X, should have an increase in margins. Basically, margin should increase for the specified recipient. In terms of the sender is basically the contract that's going to be sending risky and stable tokens into the engine, which means after the deposit's done, the sender's risky and stable balance should have decreased by the amount that a user wanted to add. And similarly, we can say the same thing about the engine. The engine is the one that's going to be receiving the funds that the sender has sent, and therefore the sender's balance should increase. Does that make sense? Any questions so far? Great. Perfect. All right, so that gives us an idea of what preconditions we need to check. So with that, I'm going to go back to the code. This action, this is the action that we're going to call. This is calling engine.deposit. We're calling the deposit function on the engine. What it takes is a recipient, the risky token, stable token, and an empty data. So I did say it was empty, and I will now go back to saying why it can be empty. The data is just going to be sent to the callback in case the callback actually wants to execute something on top of that data. Because the callback could potentially implement anything, for the purposes of this stream and for Echidna, we're just going to assume that it takes data and then just drops it. It executes as you expect with the risky transfer and stable transfer, and it does nothing else. So this is an assumption that we're making within the deposit. So if we just go down a little, we can then see this deposit callback. This is what Echidna is going to call, or what the engine is going to call when we call that deposit. It's going to take the risky and the stable token, this data, it's just going to drop it. It's not actually going to use it, and it's going to call execute callback. Execute callback, as I mentioned, is basically just going to transfer from the engine, from like the caller, in these 2 amounts. So once we see this, then we can then we know essentially the arguments that are being called. So I did say from here that margins of the recipient should increase. And so the check for that is relatively simple. We can just say, retrieve the current margin balance and make sure it's equivalent to the balance of the user of the margins for the recipient before, and add the amount that was just added. Make sure they're equal. If this is false, of course, if this is incorrect, then Echidna will fail. Another precondition we set, or another condition we said, was that the sender's risky token balance and stable token balance should decrease after a deposit. Logically, this makes sense because if the sender is the one putting money into the system. So the sender is the one who's actually going to be doing that token transfer from the sender into the engine. So what we can then test is take a snapshot of the balance of the sender after the withdrawal has happened, and assert that essentially the current balance is equivalent to the pre-deposit balance minus the amount that was transferred. So this is essentially mapping, allowing us to test that the sender's risky token and stable token balances have decreased. And in a similar way, we can say the same thing about the engine balance has increased. It's basically taking another snapshot of the engine and making sure that it's equivalent to the pre-snapshot plus the amount that we've added. Recall this entire deposit flow is basically just saying I'm as a sender, or this is a sender, putting money into the engine. We're basically making sure that that the margins for that recipient that we specified have increased, that the token balance for the sender has decreased, and the token balance for the engine has increased. Note that one difference that we did implement here was that we're using a try-catch. Try-catch allows us to test essentially the failure case as well. And I also added a link to the Solidity documentation. The reason why it asserts false within our catch is because if we take another look at our engine code, there's no other conditions that would make this deposit fail. There are only two conditions. One is that the risky and the stable token that you want to add into the engine is equal to 0, in which case it reverts. And if the token transfer didn't actually execute correctly, then it would revert. Now, with if we take a look at our own preconditions, we're always bounding the amount of tokens that we're adding into the system between is essentially always going to be greater than 1, and we're always going to mint these tokens. Therefore, we own the tokens. So assuming this behaves as a normal ERC20, it's like these tokens are always ours, and therefore it can always be transferred. So the reason why we're able to assert false here is because we know that by the time it hits this engine.deposit call, that the deposit should never actually fail. It's within safe bounds already. So we can actually consider deposit always being successful as another invariant within the system. Does that make sense so far? All right, perfect. So with that, I'm going to go into withdraw. The withdrawal, I'm going to be walking through it in a similar way, so that we can start reasoning about what is expected to hold true. With the withdrawal, the withdrawal essentially takes takes the margins of the sender, it decreases it by a certain amount. The address that's going to receive these tokens is going to be the recipient, and therefore their token balance of the risky and the stable token should increase, and the engine's token balance and stable balance should decrease. So this is the exact opposite. This is saying, before we were saying we want to change the state of the recipient. This time we're changing the state of the sender. We're basically saying the sender's balance is going to decrease um, in exchange for the recipient gaining tokens back. So with that in mind, we have an idea of essentially what we need to test here. Similar to the deposits, um, one thing that we can say is that the sender has to have a sufficient balance in order to take funds out of the system. So if they don't have sufficient balance, then this margins withdrawal is just going to revert. So we can say sender must have sufficient balance, as well as, and we go back to the withdrawal that neither amounts to zero. So again, del risky, del stable have to be greater than zero. So we can start to implement the state changes as well. So recall before what we were doing was saving essentially the snapshot of the um, pre-deposit recipient margins and all of the senders. Um, so I'm just going to just going to essentially keep a copy of all of the margin balances. So this is going to save the sender balance of the margins, the engine margins, and the recipient margins. This allows us to be able to test against it afterwards. And I'm going to do the same thing for the balances. So this is also very similar. This is a sender balances, engine and recipient balances right before. So now that we have these balances, what our pre was that the sender must have sufficient balances in the margin. So I'm just going to move that down so that we can start to implement that. If or first, and just a simple if statement check, and your margin balance of risky is equal to zero, or the balance stable is equal to zero. Um, then what we can do is just make use of the function above. We can call deposit with safe range. We can set ourselves as the recipient. Recall this is going to increase our own balances. We can increase del risky and del stable. Two is we specified there has to be sufficient balance in order to withdraw. And basically what we're saying is if there is insufficient balance or um, basically increase the balance for that recipient. Now, it brings us to the question of what to do with del risky now. Its incoming argument is a UNT 256, and because we're not bounding it, it's currently bound between one for our margins. Instead of bounding it to UNT 256, is actually just bounded between 1 and the balance that a user has. Basically saying a user can withdraw up to, from token, one token, and amount of risky token that they actually own. And we can do the same thing with del stable. This is a different bound than we normally see. This is bounding 1 to like the sender balance. So this is going to help us keep this invariant of a user has to have a sufficient balance in order to withdraw. Any questions about that so far? Right, perfect. So for the action, and I'm just going to start pseudocoding this a little bit, just so that it puts into a little bit more context as to what we're testing. The engines particularly, it's slightly different because it's going to use the margins for the message.sender, which means we want this address to be the sender. So for this, we're just going to say, okay, call the engine.withdraw function. And as usual with the recipient risky stable, afterwards it's the postconditions that gets interesting. We said already that the margin say margins to sender should decrease the withdrawn amount. We can say the recipient should increase. And obviously this goes for the risky and the stable. And that the engine's risky and stable should decrease. So what does that exactly mean? Well, that means we can now we have all the post conditions that we need to check. If we wanted to be even more verbose, then we could say the sender token balance doesn't change. Ensure that the recipient's margin doesn't change, because we should only be changing the senders, and ensure margin doesn't change. So I'm just going to group the related function or the related roles together. So that's what's above is the sender, the recipient, and then the engine's risky tokens. So now we can go into actually calling the engine. In order to call the engine, we need to, we're going to call it in a slightly different way because it relies message.sender. So this method of calling use the like low level engine.call. We're going to encode with a signature which is going to match the function signature of the provide these arguments, incoming arguments. So the recipient stable, and basically two things that can happen after this. Either it's not successful, or it is. What we can then see what is expected to happen if it's not. You know, something has gone wrong. The preconditions would have set up everything that's required for this deposit to work. Properties, what are precondition properties? They were sufficient. The sender must have sufficient balance to withdraw the amount, and that del risky and del stable have to be, which they are. They're at least one. A case in which this deposit fails, then we can assert false here because we know something has failed unexpectedly. So we've got a series. Just going to start filling in conditions. Um, we've essentially defined the sender, the engine, um, the sender. Just going to, for clarity, just to make sure they're uniform. So let's start testing the sender then. The sender, we retrieved the pre-balances, token balances of the sender with this balance snapshot. We retrieved the margins with this retrieve the margins that are in the system. To code block, take this post sender margin. So this is basically identical to the pre sender margin. It's just we're calling it a different time. Expect different. We expect that the essentially the balance should actually decrease. So what we can test there is basically that the margin, so that pre-withdrawal call of the balance risky token minus the amount that was sent out is now equivalent to the current amount. And we can say the same thing about balance stable. Here we're basically checking the sender amounts are essentially the same. There was a decrease in the margins because of the transfer, because of the withdrawal that executed. I'm going to leave the tests for didn't change for now, and I'm just going to test the changes in token balances. So with the engine, we can do a similar thing with what we did up above, but this time we're not checking the engine margin. We're checking the engine and risky stable amounts, which we can find within this balance.snapshot. So what we can then do here is save another balance.snapshot. Sorry, of the engine. I should be getting the engine. Move that down so that we have it for recipient. Retrieve the post engine token balance, and then assert on the engine's risky stable balance should decrease. So what we can do there is very similar to what we saw up above. Pre-engine token balance of the risky token minus the token that was sent out is equivalent to like the post withdrawal. So this is just to recap, the withdrawal function, it reduces the sender's margin balance, which is what we're checking here. It decreases the engine's stable and risky token balance, increase token balance. So that the recipient's token balance should have increased, which gives us something that looks like this. I'm just going brackets to limit the amount of scope. Does that make sense so far? So with that, I'm going to run Echidna. Hardhat compile. Oh, Success. While Echidna runs, I'm just going to uh, fill in how we can test how to check that these token balances haven't changed. Um, and what we can find is that it's going to be pretty much similar to these other checks. Um, what we can do is save the balance snapshot of the sender. So this is basically what we want to check. Just to recap, this is already checking that the margin sender is decreasing by the amount. What we then want to check is that the token balance of the sender hasn't changed, um, which gives us a pretty straightforward check of um, making sure that the pre-sender token balance and the post-sender token balance of both tokens are identical. So this gives us an intuition for um, how to test these particular cases. And I'll just even out the brace brackets. So I'm just going to, we can take a look at a failure case. So what we can see here is that the deposit, it says it failed within, um, and it failed, and we've got a series of revert statements. We can press escape to try to see whether there's more to the output. And basically from this, I'm just going to copy all of this into a new window. We could wrap it. Basically, what this is saying is Echidna first tried to call deposit with a safe range, and then it tried to call withdrawal with a safe range. What it's saying is this is essentially the error that it failed with. It's basically saying it tried to transfer to the zero address and reverted with transfer fail. So why would it have attempted to even transfer the zero address? Well, we can see that Echidna was able to find the case where it transferred to address 0. So this is interesting because this essentially tells us that there's a precondition that we missed. This tells us that either we missed a precondition, or the code fails to handle the case in which address 0 is a recipient. So this is something that we can then bring to primitive and kind of talk about whether that is expected behavior or not. But for the purpose of this, I'm just going to say require that the recipient is not equal to address 0. This gives us a kind of, this means that we can then create like a withdraw like to 0, where we can assume that the recipient is 0 and call the withdrawal, so that we have kind of this concrete test case. But for the purpose of this demonstration, let's just assume that the recipient cannot be 0 due to system requirements. We could run Echidna again. While it runs, I can also fill out the engine margins as well. So the engine margins, recall, we just want to retrieve the post-engine margin balances and make sure that they don't change. So we can do that by retrieving the margin balance. This is essentially getting it, and then we just want to compare that the output of the pre-engine and the post-engine are identical. This gives us this first test is checking that the stable and the risky token should decrease, whereas the engine margins are checking that the engine should be the same. Because we shouldn't ever be changing the engine's margin, because the engine is going to be holding the tokens and releasing them to a user. So I'm going to press escape again on this so that we can actually start to take a look at what. So it failed again, even though we had that zero address check added, and I'm going to copy that into just a text window so that we can figure out why this failed. So what we can see is that it called deposit with safe range. If we just take a look at the primitive engine again, it called the deposit with a recipient of this del risky and del stable. What we can see from here is that we can add a few checks within this to see, like, for example, what the output looks like. But first, we can take a look at our corpus and see what the output is. So I'm just going to go to the last one. Go to end-to-end.sol. What we can see is that it checked our liquidity and precision amounts. It hit our deposit with certain areas that have reverted, and likely these reverts are related to our withdrawals. The withdrawals we can see have hit in certain areas. We can see there are certain reverts. For example, reverts on pre-sender token balance essentially be equal, and that the margins of the sender. So from this, and then we can also check the output elsewhere. From this, we can kind of use this to narrow down where things might have gone wrong. Withdrawal, we can track these events by seeing what happened. So a transfer happened from the test token. Another transfer happened from the secondary token. So we can basically we can cross-reference this address and the token address just to compare their differences. We can see this is the risky token transfer. This is the stable token transfer. And this is telling us it's been executed from the engine. So if we break down the withdrawal with safe range inputs, this is our recipient. del risky pre-addition, like changes, and del stable pre-changes. Now, what exactly does that mean? It basically says our attempt to deposit and then withdraw from these contracts has resulted in an invariant within our withdraw actually failing. We can take a look at the coverages again, where we can double check that the balances snapshot is, so we can just walk through the conditions. First, that what happens to the sender address, so or what happens to the recipient address. So the recipient address should essentially retrieve the margins and assert that the increase in essentially the pre-deposit amounts have increased, and that the sender's balance should decrease. Wrong function. That the margin sender amount should decrease by the amount that was taken out, and that the sender's token balance should essentially be the same. What this is telling us from the output is that the recipient for this particular case is broken. As long as the risky token, as long as we check the engine balance, the difference between the engine risky and these difference between the engine risky and the amount that we're taking out should be equivalent to essentially the amount that we've as well, and the same thing for the stable. Then we should ensure that the engine margin is identical. This next check, and I'll just line this up as well, margin shouldn't change, and that the recipient is checking that the recipient balance of both tokens should essentially the recipient. So basically, what within the coverage is that there are cases in which, for example, the sender's token balance may actually change. Now, what does that exactly mean? Well, we can add logs to figure out why and what those values are. So I'm just going to add I'm going to add just after we define the values, we can just add a change in risky, what is the change in stable, and then what is the margin risky and stable balance. I'm just going to add format. We can get this automatically. And then for recipient, we can pretty much execute the same check to make sure that the recipient margins compared to the pre-withdrawal margins haven't changed. So that I'm going to let that run. At a very high level, essentially what we've done is set up the system to save balances and the margins of the engine, deposit within the engine if there's insufficient funds, take out um, that specific balance, and then execute the action, um, followed by the checks to make sure that uh, margins have decreased, the recipient's balance have increased, and that the engine's balance has also decreased. So with that, I'm just going to go back to this to display anything. I'm just to leave this as to this format. Um, One effect of using this is that it does take a little while to run. There is a fair has already been that it's already associated with it, but there are times a while. Right, I'm going to let that run, um, and we can look through the output afterwards. Um, saw within implementing these, it's a fairly complicated preconditions and post conditions that are easy to forget or easy to even just implement incorrectly. Um, so with that, it's much better to start off with all of your Echidna tests. So essentially, have the execution, and it also allows you to have a better sense for like how to split um, functions up and how to split contracts up after. Um, Another thing to that's very important is just within all of these complex systems is to take a step back, think about expected behavior in this case with the withdrawal, what is expected to happen, um, and how is that function expected to act. Um, in our particular case, it's much hard. It's very hard to reason about the changes to the changes to the margins and of these three actors. Um, so creating this kind of even just like diagramming um, what is expected to happen. Um, and another thing that comes in handy is to add custom NAT spec documentation on these functions. Its preconditions, you specify its postconditions, and if you have that all outlined within like close to the function where it's defined, you have a much better sense for what is expected to be true, and that can way that we were just adding comments throughout these streams as well. All right, so with back to the output for the withdrawal very quickly. Um, what we can see here, these are the results from, I'm going to very similar to last time, remove this format it. Basically, what we see amount is this number. Delta stable amount is this number. Margins balance sender margin risky balance is it balances. What did the withdrawal attempts to in we already established that's the risky token. It attempts to transfer in the stable, and then it calls the within this with these parameters. What we can then see is that the we're basically in which the some of the post are actually failing. And the reason for that is because if we take a look at the primitive engine within the withdrawal, there's no limitations as to um, so the recipient could in the previous case could have been address 0, in which case these arguments don't actually, in which case the arguments won't actually hold the postconditions. But it also makes no assumption for changes to whether like the recipient can't be like the sender itself, or the sender, um, or that it can't be like the engine itself. Interesting cases if we were to just play around with like the recipient can't be uh, adjusted. Um, this allows us to play around with again what that safe bound of input is, which we can then rewrite, see what the values are within the expected output. So I'll pause there for now, and take a look at quickly just the corpus. What we can see is that there are, in the case where the margins, or there are the margin sender balance doesn't and that the sender balance is not necessarily the same. So to that document, what we can see is that the Echidna address is which are depositing to a certain address with these two amounts. Then it's withdrawing to that specific address again. From that revert, we're basically seeing that the sender token balance is potentially not equal. It could potentially change after the withdrawal. And this is because the engine lacks data for tokens can be sent to the sender. So there's a series of ways that we can tweak this property. We could potentially say that the address of the recipient just can't be the address so that it can't be the message.sender, which we can continue to add preconditions to test what the expected behavior is. But in this particular case, the reason that we were getting failure cases was because the recipient was essentially equal to the message.sender, and therefore um, the assumptions on like message.sender, like token balance actually staying stable, were not necessarily held. And then this is something that you can kind of bring up to development teams and bounce to see whether that's expected behavior and whether that's something that the contracts within the contract, something within the contract should be changed or not. So we saw two different examples within last week with kind of arithmetic inverse functions this week. And then last week with internal testing, and this week with this Etheno initialization. So just to wrap up, I highly recommend going back in the primitive code base, implementing more invariants. We only touched the surface of the possible invariants within the ecosystem. There's a lot more that could be covered. We recommend creating PRs against the streaming series GitHub repo, and definitely check out the full end-to-end if you're interested. It goes through the deposits, the withdrawals, allocates, removes, and then also swaps, and touches the manager as well slightly. So there's a lot more resources to look at there, and it showcases kind of a more full approach to testing these contracts. So with that, I just want to say thank you for tuning in for the last 6 weeks. It was really fun to actually walk through these properties. Really fun just to showcase what we can do with Echidna. If you have any streams or any topics of streams that you're interested in, let us know, and play around with using Echidna on your own code base. Before I end, are there any outstanding questions? Awesome. Sounds good. Then with that, feel free to follow us on YouTube and Twitch, and look out for some new streams in the new year.